Welcome back. This video is going to be over uncertainty in data, basically looking at two things, accuracy versus precision, and also identifying significant figures and what significant figures are. Otherwise known as things that will be the bane of most honors chemistry students' existences, even though they serve a purpose in the real world. We'll talk about it in a little bit. Anyway, accuracy versus precision. In everyday usage, oftentimes they are used interchangeably, although they are not. Accuracy is defined as a measure of how close a measurement comes to an accepted value. And whereas precision is a measure of how close a series of measurements are to one another. Okay, and these example dartboards down here are kind of illustrating the difference between them, because oftentimes in common sports usage and everyday use things, people use accuracy and precise to describe a player, or like a quarterback or a basketball player's shot or what have you. Say that, oh, this person's accurate and this person is kind of precise, and they're a little bit different. So if we take a look at this first dartboard, where might be hard to see, but there's four little dots, four black dots, which kind of represent the darts or arrows or whatever you want to look at. And you see they're all grouped tightly on the bullseye here. And where the bullseye is kind of the target or the accepted value. And this would be described as both accurate and precise. Because the target, they are all basically at the target, or you could say the accepted value. And these measurements are close to one another. They're tightly grouped. Now when we look at the second one, we kind of see the difference between accuracy versus not accurate. Is that, first of all, we've got now, if you threw four darts or fired four arrows and they all landed in a grouping like this, well, one thing you would say is that, well, you're not accurate because you were trying to shoot for the target, which is here, but you are quite precise because, one, it's very repeatable. All of your arrows or darts, whatever, are very close to one another. Look at this one. You get a grouping such as this. Well, you could make the case that this is accurate, right? The target's here, and you're kind of got your data points or your darts or your arrows are kind of all around the target, but they're not very precise because they're not a nice tight grouping like this. They're a little bit less precise. And again, if you're trying to judge accuracy versus precision, typically accuracy is going, for an accepted value is going to have some sort of, like let's say the value is, the accepted value is like 2 centimeters. In order to gauge accuracy versus precision, there's going to have to be some, accuracy like plus or minus 25% or plus or minus 0.1 centimeters or something like that. You're going to need some sort of way to gauge whether determine something's accurate or not. Some type of, and that would have to be supplied by things. It's like, typically, you're not gonna, in class, I'm not gonna say, hey, is your lab measurement accurate or not accurate? You're gonna have to be given some information as far as, how close would be considered to be accurate. And this last one, you can see, you've got 4 darts at the dartboard, and one, they're not in a nice tight grouping, and they're not kind of centered around the target of what you're looking at. You would say this is not accurate and also not precise. Okay, so hopefully that gives you a little insight into what is what. And one thing that we will be using often in lab experiments, especially when we collect data and we are trying to do calculations to figure out how well we did, we're going to be something called percent error. which is kind of defined loosely as the closeness of an error to an accepted value. And the formula is given here. And again, you do not have to memorize this formula. This is on the back of your periodic table. Generally speaking, you don't have to memorize any formulas in this course. Any formula that you need will be on the back of your periodic table. One thing to keep in mind is you see here and on this side, on the numerator, those are absolute value bars. Absolute value bars. So oftentimes you will see percent error written with absolute value bars in the formula, and sometimes without. Sometimes it can be very helpful to not include the absolute value bars for percent error, so that you can have a positive percent error or a negative percent error, because that will give you some insight as far as how you did. So let's say, in this example here, 3 students are measuring density of sucrose, which is a type of sugar, and they get these values: 1.57 grams per cubic centimeter, 1.51, and 1.70 grams per cubic centimeter. And we want to calculate the percent error for each student individually. And the actual density is given as this. So this is our accepted value. Said that it should be 1.59 grams per cubic centimeter, and this are the measured values. Okay, so in this formula, this is our accepted value. These 3 are measured. So we need to do this individually for each student. So for student number 1, percent error is going to be the measured value for it. Let's say this is student number 1, this is student number 2, and this is student number 3. 1.57 grams per cubic centimeter minus the accepted value, which is the 1.59 grams per cubic centimeter. And I'm going to, for this example, I'm just going to leave off the the absolute value bars, just to see, because a negative percent error says the person measured below the target value. A positive percent error means they measured above. And this is all divided by the accepted value. So when you put this into your calculator, subtract this from this, you get on the numerator is going to be a negative 0.02 divided by that. And I would expect most of you to get something like this, a negative 1.26% error. Now keep in mind, if you come back and watch this video after we have gone through how significant figures are handled in calculations, this would correctly be reported as just a percent error of negative 1%. Okay, but this is what I expect everyone at this point in the course to report. This would be what you would report due to significant figures, and we'll talk about that later. I'm just saying, leaving this here for not so when people come back and view this, maybe to review for the test or quiz or whatever, and we've already gone over the rules for significant figure handling in calculations, you'll be like, well, wait a minute, Mr. Seymour, you did this wrong. Well, okay. This is the correct synonym of significant figures. This is what I expect people to use for today. Now, if we do the same thing for student number 2, percent error, formula 1.51 grams per cubic centimeter minus the accepted value, still 1.59 grams per cubic centimeter, over the 1.59. Do that, you're going to get left with a negative 0.08 grams per cubic centimeters in the top, and divide by accepted value, and you're going to get roughly negative 5.03%, or to the correct number of significant figures for those of you who are watching it after we've gone over significant figures calculations. Once again, you would report this as basically negative 5%. And lastly, student number 3. percent error. It's going to be 1.70 grams per cubic centimeter minus the 1.59 accepted value over the 1.59 grams per cubic centimeter. Now you notice these two, for number 1 and number 2, they were reported as negative percent errors because the measured value came in below the accepted value. This one, obviously the measured value was above the accepted value, so this one's going to be a positive percent error. And you would report this as 6.91%, or if you come back and watch this video after going through significant figures and calculations, this, to the correct number of significant figures, it would be 6.9%. Positive. Okay? Now, let us go on to talk about those significant figures. Okay, significant figures are used These are kind of for scientists / engineers. They want to measure things using standard procedure, and significant figures are used. So we'll talk about these a little more in a second, but significant figures are, for a measurement, include all measured digits plus, all known digits plus 1 estimated. And your data must always be reported to the correct number of significant figures because calculations that you use those data points for will depend on those significant figures. Now, let's go back and talk about significant figures, why they're important. So you're aware, hopefully, that anything that can measure something, whether it be a measured distance or mass or what have you, not everything is an accurate measuring device as other things, right? Most people's bathroom scales at home, a lot of them will measure to the nearest pound. A lot of them will also measure to the nearest tenth of a pound. Very few will measure to the nearest hundredth of a pound, or maybe on the less accurate side, to the nearest 10 pounds. So the data that is reported by those things are going to have the data from something that can measure to the nearest pound is not going to be as accurate as the scales that measure to the nearest tenth or hundredth of a pound. And that basically is how sensitive or how accurate your device is indicated by how many significant figures you can report in the data that comes from it, right? And that will make a little bit more sense when we get in the lab and have you measure some things so that you can kind of get the hang of things. But first of all, we want to, before we do that, for notes here, we want to be able to look at data that has been collected and determine how many significant figures are included in that data. So there's a couple of rules. First is all non-zero numbers in report data. Anything that's non-zero is significant. So you look at this value, 24.7 grams. Remember, a data is already reported a value with a unit. All these numbers are non-zero. So this would be considered to have 3 significant figures. All of those are significant. Likewise, this value here, 18.952. Well, you notice one thing that is missing on this is there's no unit, but we'll kind of disregard it. We'll overlook that for a second. Probably want to put that in for the following years. But all these values are non-zero. This would be considered to have 5 significant figures. Let's say this was in grams as well. Which one do you think was measured on a scale that was more accurate? Right? Hopefully it makes sense that this value was measured on a scale that could measure out to the thousandth of a gram, if this was in grams. This one can only measure to the tenth. And that is why this one is considered to have 5 significant figures. This one only has 3. Zeros is where it gets complicated of how to determine if something is a zero and a data point is significant or not. So all zeros that are at the end of a number are significant only if they are the end of the number that is on the right of the decimal place. Right, so looking at these values here, we've got 6.20 grams. If we're looking at this, we've got a 0 at the end of a number. You notice it has decimal place. One thing to keep in mind when you're trying to determine significant figures is if that 0 is not there, if it's not included. Let's look at this comparison here. 6.20 grams versus 6.2 grams. If I leave off the 0 on the 6.20, does it change the magnitude of the number? Does it change the value of the number? Hopefully you can understand that if we didn't include this 0, it would still be 6.2, which mathematically has the same value of 6.20. Okay? If it doesn't change the value of the number by including or that 0 or not, then that means that 0 is significant. So this 0 is significant, and these two values here are non-zero, so this 6.20 has 3 significant figures, where 6.2 only has 2 significant figures. Okay, this 0 is there for a reason. It's to communicate to you that this mass was measured on a scale that can measure to the nearest 100th of a gram. 6.2 grams says that this was measured on a scale that can only measure to the nearest 10th of a gram. And if you just saw like 6 grams, well, that scale can't even read to the nearest whole gram quantity by itself. This next one, 75.000. If you do not include these zeros, if you just kind of ignore those zeros there, well, 75.000 has the same value as 75. So the inclusion of these zeros does not change the value or the magnitude of the number. So they're there for a reason, to indicate that this was measured on a very sensitive, accurate scale. And these are significant. That 0 is significant, and so that makes all of them. Whereas this number here, you notice this is now 75,000. Well, where's the decimal place in this number? It doesn't have one. Well, it would be right here if it did have one. If you didn't include these 3 zeros, does that still have the value of 75,000? No. If you don't include those zeros, it has the magnitude of 75. So these zeros were there for a reason. They're called placeholders. Because without these zeros, this measurement doesn't have the same value. 75,000 and 75 are not the same. So only these 2 values are significant. These 3 zeros are considered to be non-significant or insignificant, and they are placeholders. Going back to this one, we've got decimal place, and we've got a 0, which is the final number, and that obviously means that this 0 is there for a reason, because 100 point has a same value of 100.0. So this 0 here was included because it's trying to tell you it was measured on something that can read to the nearest 10th. So this has 4 significant figures. Now, zeros between non-zero digits. You noticed up here above, we had those 2 zeros that were, and these 2 zeros on this number. And we don't really need to talk about those, but any zeros that appear between significant values become significant. You can kind of think of bookends, like this 1002. Well, this 1 and this 2 are significant because they're non-zero, and that makes anything between them significant. So these two zeros in the middle are significant. So this has 4 total significant figures. This one here got a 0 that is sandwiched, so to speak, between 2 significant numbers. So that makes it significant. That has 3. And this value here, these zeros are all between significant values. So these 4 zeros that are part of this number are also significant. So that has 8. So leading zeros, which appear in front of the first non-zero number, are never significant. Sorry, not first non-zero digit. They're placeholders. And one thing that you can see when we get to scientific notation later is that those zeros, if you put in your calculator and put in scientific notation, they disappear. Again, what you want to be considering is, if here's some zeros, and they're leading zeros, right? They're in front of the first non-zero number. If you do not include these zeros in the number, if it was just 253, or if you just simply took these zeros out of this number, you would either think it's a 253 or maybe 0.253. And does it have the same magnitude without those zeros present? No, it doesn't. That tells you those values were there for a reason, and they're placeholders. So these 2 zeros in front are not significant. Only these 3 non-zero numbers at the end. Likewise, this 0 here in front is a placeholder. It doesn't even have to be written. You could easily write that as just 0.123. It has the same value. Likewise here, without those present, doesn't have the same value, so they're placeholders. So that also only has 2 significant figures. Now the question is, let's say, for example, this number here. Let's say you had this number, 10.0253. Now you've got a significant number here, and you've got this 253 over here, and these 2 zeros are now between 2 significant figures, and so those become significant. And so 10.0253, everything there is now significant. You've got 6 significant figures. All right? If whenever you see something, in scientific notation, you ignore the times 10 to the whatever power for significant figure determination. You just look at what's in front. It's the things that are counted. Okay? Let me just quickly change just a sec. You always use significant figures when is measured. So you must use significant figures when some type of measuring equipment or device is used. Okay, whether it's a ruler or a stopwatch or a scale, whatever. Anytime some piece of measuring equipment is used, significant figures have to be observed. Because, like I said at the beginning, not everything has the same accuracy. And that is communicated in the data. However, if a piece of measuring equipment is not used, for example, like if I counted something, or that I have a defined constant saying that those things are considered to have an infinite number of significant figures. They were not measured. Like, the easiest example here is like if I was to count the number of students in the classroom. Let's say I count 27 students in the classroom. Did I use a piece of equipment to do that? Did I use a ruler? No. Did I use any type of piece of equipment that had some sort of accuracy to do that? No, I counted. And so this 27 students would be considered to have an infinite number of significant figures. I know exactly that there's 27 students, 0.00000, however many zeros I want. I don't have a fraction of a student, hopefully. Need to alert someone if I did have a fraction of a student. Likewise, hopefully you all know that there's 12 inches is the same as 1 foot. That's a defined constant. Just like 60 seconds is the same as 1 minute. That is a defined constant. And so those are considered to have an infinite number of significant figures. Those are, not like they're measured, they're just defined constants. So let's get some practice here on determining significant figures when we see numbers. First of all, look at this value. These two zeros here, based on rule number 4 above, those are placeholders. This 0 at the end is not a placeholder, because if this is not there, the value of the number doesn't change. So the significant numbers are these 4 right there. This case, got 2. These 4 zeros in the front are placeholders. Look at C. You've got a non-zero number here and a non-zero number there, and that makes everything in between, all those zeros in between, significant. So -5. 1430 as written only has 3. Here's the first one. Okay, this one is written in scientific, and as we mentioned up here, you ignore the times 10 to whatever power for purposes of significant figures determination. So we're only looking at what's in front. And the nice thing about scientific notation is when you see data reported in scientific notation, this tells you all these values here are significant. Makes it easy. If you see something in scientific notation, everything in there is significant. Likewise over here. Again, scientific notation, we're not looking at the times 10 to the 4th. For significant figure determination, we're just looking at this, and all of those things are significant. So it's 5. Next one. This 0 at the end, it's after the decimal place. It is there for a reason. Well, to communicate that it was something that could measure to the nearest tenth of a meter. So this is significant, but basically, same rule number 2 up above. And this 3 is significant, so that makes the 0 in the middle significant as well. So all of those are significant. Got 3 significant figures there. This value here, those are the 4 that are significant. As written, right, that has 2. These zeros here are placeholders. And you notice F and I are the same number. They're just measured with different accuracies. This was measured with something much more accurate to the nearest kilometer. This here was measured to the nearest, accuracy was the nearest thousand kilometers. Not very accurate. And then 22 students. Well, did I use a piece of measuring equipment to determine that? No, I counted it. So this would be considered to have an infinite number. Now, one last thing is that we saw this example above here about 98,000 there and 98,000 here, and how it has this way it was written as 5 significant figures, this way it was written as 2. Well, let's say, how do we handle other things? So how would I write 98,000 if I wanted it to have 3 significant figures? Basically saying, how do I write it with this 0 being significant, 4 significant figures, meaning that this 0 is significant, 5 would be all of them. So if I had to write this with 98,000, but this middle 0 here was significant, I could either write it in sign notation, 9.80 times 10 to the 4th, or without sign notation, I'd write it as 98,000 with a line over this first 0. This line over this first 0 indicates that this is the last 0 that is significant. This is saying that this 0 is significant, these 2 are not. To write this with 4 significant figures. Right, I can write it in scientific notation like this, 9.800 times to the fourth, or without scientific notation, I put a line over the middle zero. Right, I don't put a line over both of these, just the last zero that I'm saying is significant. Because this says if this zero is significant and this 8 is always significant, that means everything between it, all zeros between is going to be significant. And lastly, 98,000, and I want all 5, right? I could write it like F above, or I could write this either one of 2 ways. I could write 98,000 with the bar over the final zero, or I could write it 98,000 and then put a decimal place with no zero afterwards. This decimal place with nothing after it means that, another way of saying that it's this zero is accurate. So these 2 things represent the same number. So you'll see later on in the course, throughout the year, you will see sometimes like this, most times like this, because it's hard to find a font in Word that has a 0 with a line over it. Okay? Now that concludes this video on significant figure determination.